Hello, today we are going to continue the study of the Sturm-Louiville problem, and today we are going to talk about the self-adjoint form of the differential equation that corresponds to this Sturm-Louiville problem. So we know that the form of the Sturm-Louiville problem is the next: the derivative with respect to x of a function r of x times y prime plus q of x plus lambda p of x times y equals to 0, and some other conditions that we mentioned at the first lesson we made about this topic. But in this case we are only going to be interested in the differential equation. So you can develop this differential equation to say that this is equal to r prime y prime, or let's say r y double prime plus r prime y prime plus this thing, the same, like this. And you may think that, well, looking that we have here an r y double prime and r prime y prime, well, you can think that this is going to lead us to say that if we have a differential equation, a second order differential equation, only the ones that have the coefficient of the y prime equals to the derivative of the coefficient of the y double prime are going to be of the Sturm-Louiville problem form. But you will see that that is not true. I mean that if we have a second order differential equation, doesn't matter if we do not have the derivative of this coefficient here with the y prime. So we are going to construct a Sturm-Louiville problem equation from a general second order differential equation that has, well, this structure that we have here with the q, the p, and the lambda. Okay, so we are going to start by establishing that a of x y double prime plus b of x y prime plus q of x plus lambda p of x times y is equal to 0. So in this case, we need to establish that b is not necessarily the derivative of a. Okay, that is going to be important. So we are going to notice this expression, a of x y double prime plus b of x y prime, and we are going to construct an equivalent expression that is going to be, let's say, y prime plus b of x divided by a of x y, where of course y prime is equal to y double prime. Okay, so we here have like an expression for that will correspond to a linear differential equation that is of first order instead of the second order that we have here. So we know that these kind of expressions can be expressed as the product of, well, the derivative of the product of two functions. In this case, we are going to be looking to express this as the derivative with respect to x of the product of some factor mu times y, actually y, like this. Okay, so what we are going to do first is to multiply this expression by this factor mu as a mu y prime plus mu b of x divided by a of x y, and we said that this needs to be equal to the derivative with respect to x of mu y. Okay, perfect. So if we develop the right hand side of the equation, we will get that mu y prime plus mu prime y needs to be equal to this thing here. So we can easily see that if we compare the coefficients in this equation, we see that mu prime is equal to mu times b of x divided by a of x. So recall that mu prime is equal to the derivative of mu with respect to x, and of course this mu, well, needs to be a function of x. So we have that the derivative of mu with respect to x is equal to mu b of x divided by a of x. So we get that d mu divided by mu is equal to b of x divided by a of x dx. So if we integrate on both sides of this equation, we will get that the natural log of mu is equal to the integral of b of x divided by a of x dx, getting that mu is going to be equal to e to the integral of b of x divided by a of x dx. Perfect. So with this we have now found the integrand factor that is going to make our equation of this form that we have here, then to be able to express this thing as the derivative of a product. Something that we need to mention is that you need to remember that the Sturm-Louiville problem is defined on a closed interval a comma b. So this means that looking that we took this expression, we transformed to this other expression by dividing the function a of x here, and so that means that a of x needs to be different from 0 for all x in this interval a comma b. Okay, that is a necessary condition. Perfect. So with this we can reorder this expression as we're going to have that y prime plus b of x divided by a of xy can be seen as, well, this leads us to mu y prime plus mu b of x divided by a of xy, that is equal to the derivative with respect to x of mu y. Okay, perfect. So recall that upper y, and actually, yeah, this upper y is equal to y prime. So this is equal to the derivative with respect to x of mu y prime, little y by now. So if we go back to the original version of our equation, we had that a of x y double prime plus b of x y prime plus q plus p lambda y equals to 0. Then we saw that we can rewrite this element with this new formula, but we need to multiply by the factor mu. So this means that we are going to get, and dividing by a of x, we will get mu y double prime plus b of x divided by a of x mu y prime plus q divided by a of x, like this, plus p of x divided by a of x lambda, and then mu y equals to 0. So as we saw before, we can express this element that we have here as the derivative with respect to x of mu y, where mu is equal to e to the integral of b of x divided by a of x dx. So just to verify, if we calculate the derivative with respect to x of e to the integral of b divided by a dx y, we will get, well, let's say that this is going to be e to the integral b divided by a dx times y prime, and then plus y double prime times the derivative of this, but looking that it is an exponential function, it will be the same here, and then the derivative with respect to x of the exponent, but that is going to be the integral of b divided by a dx. So yeah, well, we can easily see that this expression is going to be equivalent to just a b divided by a, looking that, well, we're taking the derivative of the integral. So this means that we will get e to the integral b divided by a dx y prime plus y double prime e to the integral b divided by a dx and then b divided by a, which is the same thing that we have here. Recall that this is mu y prime plus y double prime mu b divided by a, exactly the same thing that we have here. So the thing here is that we can take a second order differential equation that has this lambda parameter and transform it to a Sturm-Louiville problem by multiplicating by a factor mu defined as this function over here. Okay, so let's say that if we have this differential equation, we take this, we transform it through the mu parameter, and this takes us to the derivative with respect to x of mu y prime plus mu q plus p lambda y equals to 0. So that is how we transform a differential equation of second order in this form to a Sturm-Louiville form differential equation. So we are going to see a quick example about this. We are going to work with the differential equation 2y double prime plus 6y prime plus lambda y equals to 0. You can see that, well, it is a very easy differential equation, but this is just to exemplify how to use this method. Well, the first thing we do is to divide by the function that is the coefficient of the y double prime. So this will take us to y double prime plus 3y prime plus lambda divided by 2y equals to 0. Then we identify that b divided by a is equal to 3, right? So we will get that our integrand factor mu is going to be equal to e to the integral of 3 dx, which is of course e to the 3x, and then we know that we need to multiply the whole differential equation by this factor to get that this is e to the 3x y double prime plus 3 e to the 3x y prime plus e to the 3x lambda divided by 2y equals to 0, and we can see that this can be expressed as the derivative with respect to x of e to the 3x y prime plus e to the 3x divided by 2 lambda y equals to 0, that we can identify this as the function r of x that we were talking about in the first lesson of the Sturm-Louiville problem, and this can be identified as the function p of x. So you can see that this second order differential equation now has the structure of the Sturm-Louiville problem. Okay, perfect. So this was a quick example to see how to construct this kind of differential equations. So I hope you enjoyed the lesson, and I think I will finish right now.